begin our discussion of boundary layer theory with a quick discussion of what really are boundary layers. So, boundary layers was first coined by Prandtl, who was a German aerodynamicist, and Prandtl has a lot of important contributions to high Reynolds number flows. So, whatever we are going to study is pertinent to high Reynolds number flows. So Reynolds number, as you can recall, is rho u L upon mu. So it is basically the product, or it can be also written as u L upon nu. So it is the product of the velocity, characteristic velocity. So this is the characteristic velocity. This is the characteristic length scale. So it is the length scale over which the velocity changes significantly. And nu is the kinematic viscosity. Actually, we can recast this. So the time taken for an advective process is going to be L upon U. You can verify that the units are that of second. But the time taken for diffusion of momentum is equal to L square upon nu. So if I take the ratio of T diffusion upon T advection, we end up with L square upon nu, L upon U, and this boils down to U L upon nu. So the Reynolds number, so there are various interpretations of the Reynolds number, and one such interpretation is the ratio of the time taken for momentum to diffuse to the time taken for advection. So if you imagine a hypothetical particle over here, and if this is the wall, so if we are moving with the disturbance, okay, we are moving with the momentum disturbance, so it would take this particle an amount of time. So if this length scale is L, so it would take a time equal to L square upon nu. But if we were to force this particle by means of some velocity u, the the time taken for this particle to travel a distance L would be L upon u. So this is the physical meaning. And if the Reynolds number is high, if Reynolds number is very large, it means that the time taken for diffusion is quite large. Okay, it takes more time to diffuse than to advect. And what do we mean by it takes more time to diffuse? It means that for momentum to diffuse, it takes much more time than the momentum to be advected. Okay, so momentum can be advected or momentum can be diffused. So it takes more time for it to diffuse than being advected. So if we consider the flow over a flat plate, let us now look at the flow over a flat plate. So this is a flat plate, and all these ideas of flat plate and all that can easily be extended to discussions of aerofoils and all. So it takes more time for the influence of the flat plate to diffuse upwards. So consider an incoming stream like this. So like we said, the presence of the flat plate means that the velocity at the flat plate is going to be zero. But immediately at this leading edge, so this is called as the leading edge, and this is the trailing edge. So immediately at the leading edge, only the first layer of fluid in contact with the plate will sort of feel the effect of the flat plate, and that feeling is due to the diffusion of momentum. And the mechanism responsible for the diffusion momentum is the viscosity. So immediately at the wall, the velocity profile will still be this, but very close to the wall, the velocity will become 0. So the velocity will look something like this. Now at the next level, as we proceed towards the trailing edge, there will be more opportunity for the effect of the flat plate to get diffused in this direction. Okay, so in that case, at a later profile, we would have something like this. And so the profile looks something like this. So here the gradient is sharp, here it's being smoothened out. This disturbance of zero velocity is propagating upwards. And eventually, at a much later time, it will become truly parabolic. So if we connect all the points where the velocity is the free stream velocity, we have an envelope. I mean, I've not, yeah, this is the point. Suppose. So inside this envelope, okay, the effect of viscosity is dominant. While outside, in all these regions have not yet felt the influence of the wall. So these regions behave like an inviscid flow. Okay, so it demarcates the domain into two regions, a region where viscous effects are important and a region where viscous effects are not important. This particular layer is called as the boundary layer. And typically the boundary layer is quite thin. It is 1 mm to 2 mm, and the larger the Reynolds number, the thinner the boundary layer. We will see this scaling after a while. But so if the span of the wing is suppose 2 meter, and if you know that the boundary layer is only 1 mm or 2 mm thick, you can very well say that okay, let me analyze everything as an ideal flow. We can analyze the whole thing as an ideal flow. And while this answer is partially correct, you can actually analyze everything as an ideal flow outside the boundary layer. So the flow profile outside the boundary layer can be approximated as an ideal flow. But in order to find out various important engineering parameters such as the drag or the lift, we need to accurately find out the stress. So this requires a calculation of the stress at the wall, and calculation of the stress at the wall requires an effective calculation of the velocity gradients at the wall. So if I were to draw a velocity profile, if this is u infinity, so it goes from u infinity, then it becomes 0 very quickly. So the gradients are quite large close to the wall. While if you were to approximate this as an ideal flow, this would simply be the velocity profile. So the fundamental difference between these two is the handling of the region near the wall, and that is where all the magic is. Well, the boundary layer theory was introduced for problems in aerodynamics. Its ramifications are quite large. Consider a catalyst pellet. So there is a bulk solution which has a concentration of C, and then you submerge, suppose it's a carbon black pellet. So carbon pellets are having a great adsorption property. So if I plot the concentration over distance like this, so initially the concentration everywhere is C, but very close to the surface of the carbon pellet. In fact, let me draw it from this point. Yeah. So let me call this X, and this axis is C. So initially the concentration everywhere is constant, and the moment you introduce a carbon pellet, there is a rapid decay of the concentration in the vicinity of the carbon pellet, and then afterward it becomes there is a rapid decay of concentration, and then it becomes constant. So this region is quite sharp, but very quickly, so after just a few few mm or hundreds of microns, you will see that the concentration everywhere is again the bulk concentration. So this is the bulk concentration. But because there is a concentration in the species C, there will be a very slow gradient towards the pellet, because there is no depletion of concentration near the pellet. And if you have a region where this is depleted and this is rich, there will be a migration from rich to depleted. But this diffusion is so slow compared to the reaction that such kinds of processes are called as diffusion limited reaction. And the reaction rate is purely dictated by how much mass you can bring to the vicinity of the carbon pellet. But it is only being brought about by diffusion, so the reaction rate is completely limited by diffusion. So again, this is an example of a boundary layer. A layer in which there is a sharp variation in the property, but outside that particular layer everything behaves as if the carbon pellet is absolutely absent. But in this course we are going to focus our attention on fluid dynamics boundary layer. So let me draw a clearer schematic before we proceed to the governing equation. So as we have seen, there is a boundary layer. Let us call this axis as x, and let us call the thickness of the boundary layer as delta. So delta is a function of x. Very close to the wall it is equal to 0, but as we proceed the velocity becomes the thickness of the boundary layer is 0, but as we proceed the fluid has a larger time to allow for diffusion of momentum, that is allow the diffusion of the disturbance at the plate towards the transverse direction. So the boundary layer thickness grows, and the incoming flow is u infinity. Well, there can be various incoming flows, but we will consider this prototypical incoming flow. So this can be considered as the free stream. Outside the free stream, the flow is ideal, and inside this white envelope, we have the boundary layer. And obviously here u will be a function of both x and y. And because there is a reduction in the flow rate over here, okay, that del u del x is negative. So you expect a v velocity to exist. Okay, you expect a v velocity to exist, and we'll see what that amounts to. So let us first write the continuity equation. So we have del u del x plus del v del y is equal to 0. So we are considering incompressible flow. So this is valid for Mach numbers less than 0.3. Mach number is the ratio of the characteristic velocity, that is u infinity, upon the velocity of sound in that particular medium. Velocity of sound need not be just the velocity of sound in air, it has to be rather decided by that particular medium. We can write down the x momentum equation. So rho del u del t plus u del u del x plus v del u del y is equal to minus del p del x plus mu del 2u del x2 plus del 2u del y2. Similarly, we have the y momentum equation. Rho del v del t plus u del v del x plus v del v del y is equal to minus del p del y plus mu del 2v del x2 plus del 2v del y2. So these are the three governing equations. So all this that we are discussing, these boundary layers, we assume that everything is steady, that the incoming flow is steady and whatever pattern of velocity that is formed is also steady. So if the flow is steady, this particular term vanishes. Rather, these two particular terms vanish. So we have now the governing equations for a steady flow. Let us now proceed to render these equations dimensionless. In order to render these equations dimensionless, we will choose u bar is equal to u upon u infinity. We will choose v bar equal to v upon u infinity. We will choose p bar is equal to p upon rho u infinity square. We will choose x bar equal to x upon L, where L is the length of the plate, and y bar is equal to y upon L. So the length of the plate is L. So there is nothing sacrosanct about the choice of the dimensionless parameters. We just have to ensure for now that all the terms are dimensionless. This is obviously dimensionless, this is also obviously dimensionless, and it is obvious that we only have one velocity in the problem, that is the incoming velocity, and we have only one length scale in the problem as of now, and that is the length of the plate. And this particular dimensionless number, you can recollect that it is something similar to the Euler number that we have used in potential flows, okay, or the skin friction coefficient. Basically, half rho u square has the dimensions of pressure, as you can easily verify from the Bernoulli equation. Now with these dimensionless groups, we can now proceed to render the above equations dimensionless. So let us write down. So del u del x will be del u bar del x bar times u infinity upon L. Now del v del y will be del v bar del y bar times u infinity upon L equal to 0. And this simply yields del u bar del x bar plus del v bar del y bar is equal to 0. So this is the incompressible flow condition. Now the x momentum equation. So let us divide first of all everything up by row. So if we divide everything by row on both the momentum equations, we have 1 upon row, 1 upon row, upon row, upon row. Now that will make things slightly convenient. So u del x, this will be u bar del x bar u infinity square upon L. V del u del y will be v bar del u bar del y bar u infinity square upon L. This will be minus 1 upon rho u infinity square upon L del p bar del x bar plus mu upon rho u infinity upon L square del 2 u bar del x bar 2 plus del 2 u bar del y bar 2. So from this we can divide everything by u infinity square. So we can divide everything by this parameter. So we obtain u bar del x bar plus v bar del u bar del y bar is equal to, so this row cancels out, minus u infinity square upon L times L upon u infinity square del p bar del x bar plus mu by rho u infinity by L square times L upon u infinity square del 2 u bar del x bar 2 plus del 2 u bar del y bar 2. This cancels out, so this whole thing is 1. And this L cancels out, this cancels out, so rho u infinity L upon mu. So this becomes 1 upon Reynolds number. You can easily verify this calculation at your own leisure. Now similarly, we can render the y momentum equation dimensionless as well. And in the same analogy as this particular equation, because all the scales are equal, okay, all the scales in the x and y directions are equal. It's L, it's u infinity, L. So apart from the terms, nothing is going to change about the non-dimensional nature of this equation. So the y momentum dimensionless equation will look like this. There will be as such no change. But is it really the appropriate way of scaling? So is this non-dimensionalization appropriate to the problem at hand? That is the question which we seek to answer in what follows.